Hello everybody. Today we'll discuss about plate tectonics. We know that our earth crust is made up of several lithospheric plates, and these plates are in motion with respect to one another, because of which the major features of the earth crust such as the fold mountains, the mid-oceanic ridges, the oceanic trenches, the uh, volcanic mountains, and the distribution of the earthquake belts, all these are accounted for through this plate tectonics. So let us discuss this topic. This concept was proposed by Mackenzie, Parker and Morgan in 1967, and it accounts for the worldwide interaction of the plates, that explains how the land and sea are distributed, how volcanism takes place, how earthquake belts are concentrated in few areas, and why most of the areas are not affected by earthquake. So all these features are being explained through plate tectonics. Actually, Earth presents a layered structure with upper rigid, strong and brittle layer, which is called lithosphere, and it floats over the weak asthenosphere. Lithosphere is made up of crust of Earth plus upper part of upper mantle, because we know that Earth is made up of three concentric layers: crust, mantle, core. Crust, mantle, core. So these are the three concentric layers. And when you talk about lithosphere, it is crust plus a portion of the upper mantle. Up to this length, up to this depth, the rock character is rigid. It is rigid and brittle. This forms our lithosphere. And lithosphere is actually broken into several fragments, and these fragments are in motion with respect to one another, as a result of which Earth's surface features are being produced. So we see that due to this plate motion, actually this plate motion is being controlled by the internal disturbance that takes place within the Earth's interior, the disturbance that takes place within the asthenosphere, because asthenosphere occurs below the lithosphere, which is the weak sphere, and over it the rigid lithosphere moves. So disturbance that takes place in Earth's asthenosphere or in mantle, and because of which these plates are found to get the force to be driven over the weak asthenosphere. So plates, they are the pieces of lithosphere which are in motion with respect to one another, and they account for the formation of continents, ocean basins, island arcs, volcanic mountains, oceanic trenches, mid-oceanic ridges, rift valleys and fold mountains. The interaction of these plates constitute the subject matter of plate tectonics. How the plates interact, how the plates cause deformation, how the plates contribute towards the formation of fold mountain belts, volcanic ridges, volcanic mountains. All these features are being explained through plate tectonics. So plate tectonics involves the study of the interaction of the plates and their effect. Now let us discuss about the characteristics of the lithospheric plates. So we have our rigid lithosphere, and that has been broken into pieces, several pieces, because of disturbance that takes place at asthenosphere or at mantle. These dismembered pieces, which are called lithospheric plates, they are in motion with respect to one another. So what are the characteristics of these plates? Let us discuss. Lithosphere is a rigid outermost layer of the earth that is made of crust plus a part of the upper mantle. Its thickness varies from about 0 km at the mid-ocean ridges to about 100 to 150 km thick at the oceanic trenches. So the lithospheric plate is having zero thickness at the mid-ocean ridges, because this is the site where the new oceanic crust is being created, or when new lithosphere is being created. That's why at the mid-ocean ridges, the thickness of the oceanic plate or the lithospheric plate is very thin, and it is very thick near the trench where one plate goes below the other, or where we find the convergence of two plates. There we see that thickness of the lithospheric plate is thick. So thickness is not uniform, it is variable depending upon its place, whether it is mid-ocean ridge or oceanic trench site, or convergent plate boundaries. So the lithospheric plates show variable thickness. Besides that, there are some other properties that the lithospheric plates present. These plates are core bodies, and their size and shape are not constant, not fixed. Many small plates may get united to form a large plate, and a large plate may break into smaller pieces, because we know that the plates have undergone breaking and again reunion to form continents. That has been tested throughout the geological time, and the last unification of the continents was during the Mesozoic times, when one single landmass was existing, that was Pangaea, and that has been dismembered to form the present day continents along with distribution of the oceans. So plates that we see today, they are not permanent features. They are found to change their shapes, size, and therefore it is not a permanent feature. The plates may be entirely oceanic, continental, or it may be mixed. It may be mixture of oceanic and continental plate. So these plates are floating over the weak asthenosphere, which is in fluid or plastic state or in ductile state. These plates are in motion with respect to one another and hence are interdependent on each other. They have different types of boundaries, such as convergent boundary, divergent boundary, and transform fault boundary. These three types of boundaries there are, and they are bounded by oceanic trenches, mid-oceanic ridges, and transform faults. As the plates are core bodies, their motion causes rotation, and this rotation takes place with respect to the axis of rotations. Plate margins get deformed during interaction of plates. The oceanic plates are created and destroyed, whereas the continent plates are not destroyed. The plate boundaries are not permanent features. These are found to change during construction and destruction of plates at different margins. Plates are having velocities which vary, and it is about 1 to 6 centimeter per year on an average. Again, within a plate, different parts have different velocities, as plate motion is circular, and this takes place with respect to an axis of rotation. Farthest the boundary of the motion from the pole of the axis of rotation, more is the velocity, and that near the pole of rotation the velocity is negligible or zero. The margin of the plates are the sites of seismicity, volcanic activity, deformation, metamorphism, and upheaval. And the interior of the plates are found to be free from deformation. Now, we will discuss about the plates, what are these plates and how they are being distributed, or how they are distributed. So, distribution of plates. There are 7 major plates, or we can say 6 major plates, or there are 7 minor plates and many micro plates. If you take America as one plate, it will be 6 plates, or if you take North America, South America, 2 plates, then there are 7 major plates. So 7 major plates, 7 minor plates, and many micro plates are there. So what are the major plates? North America, South America, Africa, Eurasia, India and Australia, Pacific and Antarctica. These are the 7 major plates. Beside these, we have the smaller plates such as Nazca plate, Cocos plate, Scotia, Juan de Fuca, Arabian plate, Philippines plate, and Caribbean plate. So these are the 7 minor plates. Beside these, we have many smaller plates. Now let us know what is the difference between boundary and margin of the plates. What is boundary and what is margin? So lithospheric plates, if this is a plate, these are the 2 plates. So the superficial trace is the boundary. Superficial trace between the 2 plates is the boundary, and this whole surface is the margin between these 2 plates. So this is the margin, and this only superficial trace is the boundary. And based upon the superficial trace, we have classified the boundaries to be convergent, divergent, or transform fault types. So margin represents a planar body. It is a line. Boundary represents a line. And we have these 5 types of boundaries, such as convergent or destructive boundary, or consuming boundary, or it is otherwise called sinks, divergent boundary, or constructive boundary, or accretionary plate boundary, or sources, transform fault, or conservative boundary, or shear plate margin. Then we have convergent transform, then divergent transform. So these are 5 types of plate boundaries, but major is convergent, divergent, and transform fault. These are the major, and mixture of convergent plus transform fault. This is convergent transform. Mixture of divergent plus transform fault. This is divergent transform fault boundary. So these are the types of boundaries that the lithospheric plates present. So here we have the plates, the major plates, North America, South America, Africa, Eurasia, then India and Australia, the Pacific plate, then we have the Antarctica plate. These are the major plates. Besides that, we have the small scale plates, Nazca, Cocos, Caribbean, Juan de Fuca, this Arab plate, we have Scotia plate. So the Philippines plate. So these are some of the smaller plates. And these plates, they are having different types of boundaries. This is the divergent plate boundary. Here, this Pacific plate, it is having convergent boundary. And here we have the transform faults. Here we have the transform fault boundary. Here transform fault. Here we have the transform fault boundary joining Juan de Fuca and the Juan de Fuca plate reach. This reach to this the Pacific plate boundary. So these are the plates, they are distributed over the globe, and these are the major and minor plates and their boundaries. So we have the 5 types of boundaries, and let us discuss them in detail. Let us discuss first the convergent boundary. The convergent boundary is the boundary in which two lithospheric plates come together. The lithospheric plates, as we have discussed, lithospheric plates may be entirely oceanic, may be entirely continental, or it may be mixture of continent and ocean. Pacific plate is entirely oceanic, and other plates are more or less of mixed type. And how they converge, let us discuss. These plates, as we are having 3 types of plates, so we can think of their convergence in that, that is, it may be continent to continent, it may be continent to ocean, it may be ocean to ocean. Oceanic plate with the oceanic plate, oceanic plate with the continental plate, continental plate with continental plate. This type of convergence that can be expected. So let us discuss continent-ocean convergence. For example, Nazca, South America, Cocos, South America, Indian plate and Eurasian plate at Sonda Trench or Indonesian arc Juan de Fuca and North America, Mediterranean Sea with Eurasia. So these are the convergence between continent and ocean. Nazca oceanic plate, continental plate. Caucasus oceanic plate, continental plate. Then Indian plate is having oceanic part towards its north, and it is having its contact with the Eurasian plate at Sundar Trench. Then Juan de Fuca plate, the oceanic plate, then North America continental plate. So we have the continent ocean convergence, and these are the examples. So what happens when a oceanic plate converges towards a continental plate? We know oceanic plate is dense, heavy, and therefore it bends and descends below the continental plate. And this process of motion is called as subduction, because oceanic plate bends and goes below the continental plate. This is continental plate, this is oceanic plate. Because it is heavy, it will go bend and go down, and this process is called subduction. And by this process, we find many features, development of many features in continental ocean convergence. These are the trenches, forearc region or forearc basins, accretionary prism, volcanic islands or island arc, andesite lines, back arc basins, Benioff zone, ophiolites, batholiths, paired metamorphic belts, volcanoes. So these are some of the major features that develop due to ocean continent convergence. So what is trench? Trench is produced when a heavy oceanic plate bends to move below the continental plate. This is continental plate, this is oceanic plate. Oceanic plate bends, this is the boundary, continental plate and ocean plate, here it bends. So here it forms a deep basin which is elongated in this manner. This is between these two plates from this bending zone, and this depression, long linear depression that comes into picture because of bending of this oceanic plate at the boundary of the continental plate, this produces a depression which is called as the trench, oceanic trench. And we have the trenches that may vary in their depth, and we have very deep trenches in the world, such as your Mariana Trench. We have the Mariana Trench is the deepest trench of the world, and we have also the very long trench, Peru Chile Trench, one of the longest trench that has been produced because of the convergence of Nazca plate with the south American plate. So trenches are long, linear depressions that develops due to the bending of the oceanic plate with the at the boundary of the continental plates. So trench is produced when this heavy oceanic plate bends to move below the continental plate. It forms a long deep basin between ocean and continent plate. This is the site of negative gravity anomaly, such as Tiruchilli Trench, Sunda Trench. The descending oceanic plate under increasing temperature pressure conditions gets gradually melted to produce magma, which intrude into the overriding continental plate to produce volcanic arc or island arc or continental arc. This arc is convex towards the ocean and concave towards the continent. Because we know that oceanic, we know all the plates. The plates are not planar bodies, the plates are curved bodies. So this is, let us say, this is oceanic plate. So this is going down. And when it is going down, this surface is facing resistance with depth. That's why it will be melted in this manner. In this manner. And this melt will come up. Thus, if it is the oceanic plate, it will create a volcanic feature like this. So, this feature, this volcanic mountain which is being created because of melting and subsequent extrusion of magma or lava to produce this volcanic arc is having a shape which is convex towards ocean, concave towards continent, because it faces resistance. It is curved. It faces resistance, so it moves, melts in this manner. So it becomes like this. So this melt comes up and it gives rise to arc-shaped islands. That's why these arcs are convex towards the ocean, concave towards the continent. So this arc which is being produced is found to convex towards ocean and concave towards continent. As oceanic crust is basic in composition and its melt produced is basic in nature, this magma, while intruding through the continental plate, mixes with the granitic rock and sediments, and the magma composition changes to andesitic or rhyolitic, and therefore andesitic rocks are produced. And we find the volcanic arcs to be andesitic. The boundary of this arc towards the trench forms the andesite line, which separates the basalts of the oceanic crust or rock types towards the trench from that of the arc rich in rhyolite, andesite or granitic rocks of granitic composition. Example, the Andes Mountains. So, we see that the oceanic plate that bends down below the continental plate, it melts, it produces magma. That magma is found to erupt through the continental plate, it melts continental plates, it mixes the sediments with of the continental plates, and its composition changes. That's why the volcanic arc which is being produced is found to be rhyolitic or andesitic in composition. And this composition is found to be closer towards this composition is found to be closer towards the continent, and towards the oceanic side, the andesites, they separate it from the basic oceanic crust. So towards ocean, we have the boundaries of these volcanic ash represented by andesites, and these andesites, they produce a line which we generally call as the andesite line. It separates, this andesite line separates the basalts of the oceanic crust or rock types towards the trench from that of the arc, region, rhyolite, andesite or granitic rocks of granitic composition. The region in front of the volcanic arc, the region in front of the volcanic arc towards the trench forms the region where four arc basin is found, or this basin is called four arc basin. So it is the region in front of the volcanic arc towards the trench. The sediments present in the trench are compressed, folded and piled up against the continent to form accretionary prism, because the oceanic plate is going below the continental plate. So the sediments which are being laid down at the boundary zones are being compressed, and they give rise to accretionary prism attached to the continental side. So this is the accretionary prism. This is the oceanic plate which is going below the continental plate, this continental plate, and here the magma is being produced. Magma goes up, produces a volcanic arc, and here this is the arc. Arc is like this. So this portion is representing the four arc basin. So let us see that with descending of the oceanic plate down and down into the asthenosphere, lower or the lower mantle, it is melted, and hence the margin of the oceanic plate is found to be destroyed, and that's why this type of boundary is called destructive margin or sinks. The magma generated by this melting of the oceanic plate may give rise to convection current below the overriding continental plate, causing its thinning, stretching, and finally converting the continental plate behind the volcanic arc to form a basin known as back arc basin. So this is the diagram. So here the oceanic plate is going down, and we know that this is the arc. Here the arc is being produced. Here it is the arc. So the arc will be like this. Will be like this. Because the plates present curved bodies, curved margins. A plate presents, if this is a plate, this is this type margin, shape of the margin of a plate. So if it is going down, it will face resistance and it will face melting in this manner. So it will have a arc-shaped feature that develops because of the melting of this plate and subsequent intrusion of the magma to produce the arcs. So here the arc will be like this. With this plate is going down, the surface feature, its boundary is like this. The margin, the plate margin like this, margin faces resistance, so it moves like this, it melts like this, and that's why it is being erupted like this and it produces arc like this. So it is convex towards ocean, concave towards continent, and this magma which is being generated here and it is found to intrude into the continent side, it will produce the arc, the volcanic arc. If it is attached to the continent, it will be continental arc. If it is separated and is found within the sea, then it will be island arc. Normally it is volcanic arc or continental arc. And this magma which is being generated here and is erupted, that may have a convection current like movement towards the continental side in this manner, so that the continent side is found to be subject to tension, stretching, thinning, as a result of which this type of basin may be created because of the convection current that develops from the magma that rises upwards. They may give rise to this convection current like feature which will drag this continental part, will make it thin, finally they will be ruptured, rifted to form the back arc basins towards the continent side in front of the arc. So see back arc basin, here we have the fore arc basin, and these are the features which are found to be associated with ocean continent convergence. Now it is generally observed that the subduction zones are the sites of the origin of wide range of earthquakes, starting from low focus to deep focus earthquakes, which are concentrated in a narrow sloping plane or zone from the trench to the margin of the subducting plate. This sloping zone is called as the Benioff zone or Wadati Benioff zone. We know that the ocean plate subducts like this, it bends at this portion. So from this point, or we can say from the trench side to the margin of the descending plate in a narrow zone from the surface downwards like this, starting from this trench up to this margin, we find a narrow zone over this subducting plate, which this subducting plate is facing resistance because it is going down against the resistance of the mantle. So these surface parts of the descending plate at the sides where shallow to deep focus earthquakes are created, or this is the site of the focus of the earthquakes, and this zone, because of these occurrences of earthquakes, are described to constitute a zone which is called Benioff zone, noted for origin of the earthquakes. Either it may be deep focus earthquake, it may be shallow focus earthquake. So this Benioff zone starts from the trench to extends up to the margin of the descending plate in a narrow zone on the surface of the descending plate. During this convergence of the oceanic plate with continental plate, the marine sediments of the oceanic plate may get compressed, crumpled, and deformed. It will give rise to the accretionary prism. And it may so happen that the oceanic plate which goes down the continental plate, the slabs of the oceanic plate may be scraped off by the overriding continental plate, and this may get incorporated into the chaotic mass of complexly deformed rocks called melange, meaning a jumble. That means when the oceanic plate is going down, here is the continental plate, oceanic plate. Parts of the oceanic plate may be scraped up, may become a part of this zone. It may be mixed up with these sediments, continental rocks, and this oceanic rock. They may get mixed up to produce a mixture of rock, a melange, and this is jumble. And here it is described as the abducted complex rock, and it is otherwise called as the ophiolites. So here what we see, that dense deep oceanic rocks may be thrusted up in the mountain masses and can be exposed at the earth's surface. This process of exposing oceanic rock is called abduction. Within the melange, distinctive assemblages of deep sea sediments, submarine lavas, barytitic and gabbroic rocks, together with the oceanic crust, produce ophiolites. These assemblages look like snake skin, and hence ophiolite is called a snake rock, which is produced by abduction. Thus we see that when the oceanic plate is subducting below the continental plate, a portion from its top may be scraped, may be mixed with the continental plate, and this mixture may be produced through abduction, and the mixture is called ophiolite. And a typical ophiolite shows the following features. Layer 1 is sediments Layer 2 is represented mafic volcanics, pillow lavas, margins with mafic sheets. Layer 3, high level intrusives that may belong to tungstennite and gabbroic. Layer 4 is the most discontinuity, represented by olivines, gabbro, pyroxenite, peridotite, and below it we have the upper mantle represented Habsburgite, lazulite, dunite. So mixture of these rocks together. So these parts are the parts of the oceanic rock, and here the sediments laid down in the continental margin. Mafic volcanics, they all get mixed up to produce this snake skin rock, which is otherwise called abduction, which is otherwise called ophiolite, and this is produced through abduction. Besides ophiolites, the convergent boundary zone of the continent and ocean may be characterized by fold mountain belts, which form due to compression of the oceanic sediments with the continent during convergence. For example, Nazca, South America, they have given rise to Andes. This may be accompanied by upheaval of the folded rocks to form fold mountains with core portions represented by magmatic bore rocks, intrusive rocks made up of basalts, gabbro, or diorite or andesite, rhyolite or granite in composition that forms the core of the fold mountains, and they give rise to batholiths as huge intrusive bodies of igneous rocks. So fold mountains are produced because of the ocean continent convergence, and the core portion of those fold mountains may be represented by igneous intrusives, igneous bodies. Another important feature of the ocean continent collision is that develops paired metamorphic belts near the trench because of high pressure of the subducting plate. High pressure, low temperature metamorphic rocks are produced, while away from the trench towards the land plate because of magmatic activity, high temperature, low pressure metamorphic rocks are produced. Thus, paired metamorphic belts are common features which are found in ocean continent convergent zone. The convergent boundaries are also noted for the volcanoes. There are some volcanoes which are found to come up during these convergence of oceanic plate with that of the continental plate. Such as for example, in case of Nazca, South America, we have some of the volcanic mountains or Cotopaxi, Chimborazo, Elbesti, Ubinas, Lascar, Laima, Lulaico is the highest active volcano at Argentina Chile border. So these are the mountains, volcanic mountains which are found in Nazca, South America convergence. Similarly, in case of Juan de Fuca, North America boundary, we have the Cascade Mountains. We have the St. Helens Mountains, Hood, Shasta, Majama. This is Crater Lake. So we see that these convergent boundary zones are dotted for some of the volcanic mountains. Thus, the convergent boundary zones between the ocean and continent are highly important with respect to oceanic trenches, venue of zones, fold mountains, volcanic mountains, paired metamorphic belts, andesite lines. So these are the main features that are found to be associated with ocean-continent convergence. Then we will discuss about ocean-ocean convergence.